Hello everyone. In this session, we are briefly going to discuss about what Softmax activation function is and how is it different from the Sigmoid function that we have already dealt with during our logistic regression implementation. So in case of binary class classification problem, we always have considered one single neuron in your output layer. Your output layer always had one single neuron, and whatever z value that you have computed, whatever logit value that you have observed at this particular neuron is being sent as input to your sigmoid activation, which generates these values which are ranging in between 0 to 1. So when I say z as logit value, the logit value here is the output of the linear transformation, which is W transpose X plus B. So whatever inputs that you receive from its preceding layer, you just take the summation of it, the weighted sum of it, and add the bias term to it. So that resultant output is going to be the logit values, which is denoted by z here. Okay. So this is being sent as an input to your sigmoid function, which again squashes whatever logit value that you have into bounds of 0 to 1. And we have interpreted this to be the probability of yi being equivalent to 1 in case of a binary class problem. So if at all the value is 0.70, then the probability is 0.7 that the particular observation belongs to target class equal to 1. That's how you interpreted the whole thing. So now in case of multi-class classification problem, you no longer have one single neuron in your output layer, but rather you have multiple neurons like I have depicted here in this particular diagram. So in this particular diagram, your target variable basically had three different labels or three different categories associated with it. 0, 1 and 2. I'm considering the labels as 0, 1 and 2. It could be either of these. So for every label, you are now having a different neuron. So whatever outputs or logit values that you are observing at individual neuron, which are represented as O21, O22 and O23, so all of these logit values are now presented to a softmax layer. I can call this a softmax layer. So this softmax layer or softmax activation to be more precise considers all of these raw logit values as inputs and then transforms or generates these values which we call as P1, P2 and P3, which we can consider them to be relative. So all of these probabilities, like P1 indicates that the probability that your yi belongs to class 1, yi belongs to class 2 and p of yi belongs to class 3, considering the labels are 1, 2 and 3 and not 0, 1 and 2. Okay. Now all of these individual probabilities are completely relative to each other. Hypothetically, if this particular probability is 0.70, this could be 0.20 and this could be 0.10. When you sum up all of these probabilities, it will be equivalent to 1. That's what relative means here. Instead of considering softmax layer here, if at all I consider a sigmoid function, whatever O21 that I had, whatever output that I had, whatever logit value that I had, if at all I'm passing it to a sigmoid function, this is going to generate again P1, which is bound in between 0 to 1. The range of these P1 value is going to be in between 0 to 1. Let's say that the value is 0.68. Similarly, sigma of O23 at every layer, at every individual neuron in the output layer, instead of presenting all of these logit values to softmax layer or softmax function, I am passing individual values to the sigmoid function now, which generates these probabilities P1, P2 and P3, which are again ranging in between 0 to 1. So this P2 could be 0.89 and this P3 could be 0.23. So these are mutually exclusive to each other. They are not relative probabilities. Since we are treating every output here as independent with each other, right? Whenever you are taking the sum of all of these probabilities, it's typically greater than 1. And this is not what we expect. So we want the probabilities to be generated in a relative manner so we can easily perceive what is the target label or predicted label for that particular observation that you are currently tracking, right? So here you could not make out whether that particular observation belongs to class 1 and class 2. Since class 1 probability value and class 2 probability values are typically greater than 0.5, you do not know what is right here. So instead of all of this, if you had relative probabilities like earlier, like 0.70, 0.20 and 0.10, we clearly know that P1 here has got the maximum value and the predicted label here is going to be label 1. So that's how you can interpret all of these outputs. So softmax function is going to typically help us consider all of these raw logit values as inputs and then generates these relative probabilities that you can compare and then make a decision about your predicted class label. Okay. What if I generally have all of these values with my sigmoid activation function itself? Let's say that sigma of O21, sigma of O22, and sigma of O23 here are going to be the probability values of 0.70, 0.89, and 0.23. These are the outputs, right? So if I normalize all of these values like 0.70 divided by 0.70 plus 0.89 plus 0.23, and then similarly, whatever value that I obtain here, I just place it here. And for the subsequent calculation, I consider 0.89 divided by 0.70 plus 0.89 plus 0.23 and have this value here. And obviously for the third calculation, the numerator will be 0.23 divided by summation of all of these values. So when you take the sum of the resultant values, it's going to be 1. Just typically have normalized all of these output values. But it really doesn't make any sense. Why doesn't it make any sense? Because your logit values can also be negative in nature. Whenever your logit value is negative, here the P2 value which you are considering to be probability value will also turn out to be negative. Your probability values can never be negative in nature. That's one of the biggest problems of normalizing the outputs that are generated from the individual sigmoid functions that you are having. And hence, considering softmax is very critical. Softmax generally considers these exponent values. So whatever logit values that you had, let's say that 2.0, minus 2.0, and 0.1 are 3 different logit values which are corresponding to O21, O22, and O23 that we have seen in the previous slide. Now we are calculating the individual probabilities as like e to the power of 2.0 divided by summation of I equal to 1 to j, or probably instead of writing this as summation, I can simply go about considering e to the power of 2.0 plus e to the power of minus 2.0 plus e to the power of minus 0.1. Okay, so any negative logit value now is going to be positive in nature, since e to the power of any negative value is always going to be a positive value. And that's how softmax caters to any of the negative logit values that you are having and translates into the output values which are relative to each other. And sum of all of these relative values is again going to be equivalent to 1. Okay, so let's try to implement this in Python. So we are very much well versed with what we have been discussing so far conceptually. Okay, let's consider these values as raw logit values. Let me create a simple NumPy array. I'm providing values as 2.0, minus 1.0, and 0.1 for O21, O22, and O23. Right? Let me also print Z array that I have just now computed. And once we have the input data for your softmax, right? So we need to find what it outputs could be. So I have not yet coded any function for softmax yet. So let's write a user defined function, call it as softmax, and it considers Z as input as one of the parameters to be more precise. Now I'm going to write a return statement, which is going to be np.exp Z divided by np.sum of np.exp of Z. I'm just typically implementing the exact formula that I have shown to you. E to the power of x divided by summation of I equal to 1 to j, e to the power of zj, whatever you call it. Right? Just taking exponents of these individual logit values, taking a summation of it, then using it in the denominator. That's all. Nothing fancy here. So once I have executed this particular statement, let me call this particular function by passing in this Z array that I have defined in the previous step. Now you clearly understand whatever particular output had highest absolute positive value. So 2 was the highest value among all these 3 values that you had, corresponds to having a probability value, which is way higher when compared to the other 2 probability values here. Even if you are taking the sum of all of these outputs, I'm calling this as outputs or outs, whatever you call, or probabilities to be more precise, right? And when I take the sum of all of these probabilities, it's going to be equivalent to 1. np.sum of all of these probabilities is going to generate a value of 1. Okay. The same can be implemented using PyTorch. Okay. Let me recreate this particular Z, but instead of creating it as a NumPy array, Let me call it as torch.tensor. And this time I'm going to pass multiple observations. So I'm having multiple observations for which there are different logit values that are generated. So let me call this as like 0.1, 4.0, minus 2.0. Okay. So now I have created a tensor object, a two-dimensional tensor object to be more precise. Now torch.softmax is going to help me compute the corresponding probability values for individual observations that I'm having. Okay. So dim is equal to 1 along the axis of 1. So dim is equal to 1 indicates that I need to apply the softmax along the axis of 1. Now you clearly understand these probabilities are matching. The very first row that you are observing in this output tensor matches with our previous calculation that we have done, since these values are matching with the first observation logit values here. Okay. And however, when you are observing the second observation's logit values, so we clearly know that this second element had got the maximum value, and hence it is bound to have the maximum probability value, as we can observe here in the output. 0.9778 is the probability value that corresponds to this particular observation logit values. Since this is maximum of all, you are having the maximum probability. And since this is minimum of all, minus 2.0 is minimum of all, you are having a probability value of 0.0024. That's how you need to interpret it. So we clearly have understood the difference in between softmax activation function as well as sigmoid activation function, and why we are not using sigmoid function at individual neurons in your output layer, and why we are only restricting ourselves to using softmax activation in case of solving multi-class classification problems here. And we also have implemented the same in Python by defining a user-defined function, also by leveraging the existing function called softmax, which Torch is offering us. And we typically have considered these different logit values pertinent to different observations within your data, right? There could be n number of observations that are presented to the network. Every observation will have their corresponding logit values presented to your output layer. That's what I'm considering here. Okay. So you have two observations, and hence I'm having two different records here. Each one corresponds to the logit values of a particular observation, and applying softmax on this along the dimension 1 is going to result in the probabilities associated with individual observation that's presented to the network. Okay. In the next session, we are going to learn more about what cross entropy loss is and what binary cross entropy loss is. How are they different from each other? For multi-class classification problem, what is a loss function? What is a generic loss function that we are going to use, and how do we implement that in Python? All of these concepts we are going to touch base in our subsequent session. Okay, so that's all in this particular session, and thanks for watching.